Hi, everybody. Welcome to Geography, our last geography class of the summer. I'm happy that you guys are all here. We've had fun this summer talking about maps and talking about the real world that they represent. Last week, we talked about the way that maps try to represent the real world and how they often kind of distort what the real world looks like, such as in this map. We talked about how small Greenland actually is compared to the rest of the map. I think it was a lot of fun. I hope you guys had fun too. Hi, Evan. Hi, Leah and Cian and Ian and Milo and everybody else that's coming into the class. Milo has a great question. Are there classes tomorrow? No. I know that in James's class, he said that there was. He made a mistake. He didn't realize that today was the last day. So sorry about that, but today is the last day of classes. We broadcast from Delphian School in Oregon, and our summer session is coming to an end. So we have to kind of end off our online classes too. But we will be back this fall in some form. We're figuring out exactly what's happening right now with the regulations and what's happening in the world with school and if it can be online or offline or what's all. That's all a little bit up in the air right now. But we will be back this fall in some form. We will be sending out an email to all of you soon. So I'm very sad that today is our last day of online classes for our summer session, but we will be back this fall. Hi, Arnav. Hi, Aubrey. Hi, Ethan. Hi, Tanisha. We'll miss you too, Tanisha. We're so happy that you've been here for the summer classes. Milo has a question about our short story in our collection from our creative writing class. I will be sending that out. I'm trying to send that out today, actually, get that done. So that's all I'll say about creative writing. Willow has really liked our classes. Awesome. We're happy you've enjoyed them, Willow. All right. Are you guys ready to talk about geography? I hope so, because we're going to be doing something fun today. We're going to be talking about something called plate tectonics. What the heck does that mean? Well, plates aren't just dinner plates. Plates can also be big chunks of things like the surface of the Earth. The surface of the Earth is actually composed of big chunks that we call plates. And what does tectonics mean? Tectonics comes from an old Greek word that, as far as I can tell, means how things are built or how they're kind of put together. So plate tectonics, if you've ever heard that term, it kind of just means how the world, like you can see behind me in this map, is kind of built or put together, the surface of it, with plates, big chunks of earth that kind of move around. We're going to talk about that a little bit more in a little bit. Milo, you are right. Earthquakes are part of plate tectonics, and we're going to get to earthquakes in a little bit too. Oh, that's very sweet, Willow. I'm glad that you like the classes. Aubrey says there are also plates on the back of a stegosaurus. Yes, that's a different type of plates, but it's very similar in that they're sort of flat chunks of something. The dinner plates we eat off of are like flat pieces of something. In the same way, there are plates on a stegosaurus's back. Back in the old days, in the Middle Ages, we would talk about knights would have plate armor. So plate, the most simplest form of it, is just sort of like a flat chunk of something. And the surface of the Earth has flat chunks of things too, which we'll talk more about in just a moment. Okay, first off, where are we? You are here. This is the Earth. It's a ball. We've known that the Earth is a ball for thousands of years. The idea that the Earth is flat has kind of come and gone throughout history. I think a long, long time ago, people thought the Earth was flat. Nowadays, some people apparently think the Earth is flat again, which is pretty wild because scientists have been able to prove that the Earth was flat for literally thousands of years. There's a lot of ways that scientists have figured this out. The earliest scientists that figured it out, they were able to make some calculations thousands of years before we had computers or airplanes or anything. All they did was they were able to tell based on shadows. They would have things that stuck up and down, and they could tell that closer to the center of the Earth, the shadows, there would be no shadow on something because the sun was directly overhead, basically. But further away from the equator, that same time of day, something sticking straight up would have a little bit of a shadow. And from that, they were able to tell, okay, if the sun is right overhead here, but like 100 miles away, there's a shadow, that must mean that the Earth is actually curved. If the Earth was flat, there should be no shadow in both places at that time. So they were able to use math a few thousand years ago, and they actually figured out the circumference of the Earth, like how big around the ball of the Earth was. Some people feel like you might have heard that some people, like in Columbus's time, when Columbus sailed across the ocean, that they thought the Earth was flat. No, back then they actually knew that the Earth was a globe too. Throughout most of the past few thousand years, anybody that had a little bit of education was, knew that the Earth was a globe, that the Earth was a ball. Ian has a good point. It's not a perfect sphere. It's not a perfect mathematical sphere. Because the Earth spins around, it actually forces the middle part of the Earth to have a little bit of a bulge. The Earth is a little bit wider than it is tall. Like a perfect mathematical sphere would be like the same distance from, top to bottom, side to side, front to back. The Earth is a little bit fatter around the middle. Yes, and Isis makes a really good point too, that we have pictures of Earth now. We've actually been able to send people up into space, and they orbit around the Earth and they take pictures like this one. And, we know that the Earth is a ball. But while we can look at that and see that, what is inside the Earth is a lot tougher to figure out. A lot of people throughout history have had different sort of ideas about what was inside the Earth. We knew the Earth was round, but we didn't know what was inside. Some people thought that the Earth was hollow inside. Up here is a picture of this blue line here is like the outside, and they thought there was maybe like a whole kind of another world inside. There's a really famous book called Journey to the Center of the Earth. They've made several movies out of it. It was written by a guy named Jules Verne. He thought maybe you could go down through holes in the Earth. I mean, it's a fictional book, but in the book, they thought maybe there was like dinosaurs and cool stuff inside. This picture here is pretty wild. Apparently, I couldn't tell if this person was serious or not, but this is like a cutaway. And this person apparently thinks that we live on the inside of the Earth. Yeah, I know. Like here's the oceans, here's the land, and imagine a ball, but we live on the inside of the ball instead of the outside. And I guess the sun is like in the middle of the ball. It's pretty wild. This is just a really fun painting down here of what some people thought the inside of the Earth might look like giant caves full of light and rivers and oceans and stuff. This picture is a very old-fashioned picture too, where another person thought we live on the inside of the ball. Instead of living on the outside of the ball, and when when a boat sails away, you kind of see the boat go down and down and down. Like you'll see the boat going over the horizon because the Earth is curved. This doesn't totally make sense because if the Earth was curved this way, you'd kind of see it go up. Anyway, it doesn't really make sense. Wow, Ethan has been doing our classes since they started in April. Ethan, you've been around like the whole time. That's awesome. Yeah, so a lot of people, a lot of different ideas about how the Earth looks or what might be inside the Earth. But scientists, Euron asks, do they take pictures in the internet? Yes, they take pictures from the International Space Station. It's actually pretty cool. You may have seen this from James's space science class, but they just have cameras and they can just take pictures of the Earth as they go around it. It's really cool. Katya has been here since April too. That's awesome, Katya. Thanks for coming to so many of our classes. Okay, so to talk about the surface of the Earth and the plates that make it up, we kind of have to go way back and talk about where the Earth came from. Billions of years ago, there's just lots of, we're kind of jumping into James's territory here. We're going to talk about space for a little bit. But planets form out of, there's lots of like dust and matter just kind of in space. And because of gravity, all the little bits of stuff kind of want to stick together. Big chunks of stuff would kind of bounce against each other and maybe kind of stick together and form into bigger and bigger balls of stuff. Scientists now have a pretty good idea that in the early history of our solar system, enough stuff stuck together that it formed, like this is what the Earth looked like billions of years ago. It was like a giant hot ball of like molten, which means like melted like rock. I read, it was really interesting. Apparently, scientists think that it kind of cooled down and started to form an atmosphere, like air around the Earth. And then another giant chunk hit it really hard and blasted a lot of matter out into space. And that hit created so much force and energy, it like superheated everything that was here. If you like rub your hands together, you feel your hands get hot, right? It's because when things rub together, that friction creates heat. So a giant ball of matter hitting the early Earth created so much impact and energy that it heated everything that was in the Earth up. So we had this giant like molten ball of like iron and other like, elements. But over time, the outside of it, because space is very, very low temperature, just out in space in general, there's not very much heat. The outside of the Earth started to cool off. If you imagine something like baking in your oven and it's all, like cake batter and it's all, molten and it's like melted kind of, and you take it out of the oven as it's baking, it starts to cool off. It'll be when you first take it out of the oven, it'll be like soft and, a little bit squishier, but as it cools, it hardens. So as you can see in this picture, the outside of the Earth was hardening. It was turning into like hard rocks. And it kind of, like in this picture, you can see sort of the hot lava looking stuff inside and then the harder, cooler rock on the outside. This is the Earth billions of years ago. Over long periods of time, the atmosphere formed around the Earth again. Liquid water, like there's water vapor, hydrogen, oxygen, it formed and collected and it created water on the surface of the planet, oceans, life eventually formed, plants, animals. And this is a cutaway now. This is sort of like a sideways view, but we ended up with something like this. The very inside of the planet, scientists are best idea of what's in the middle of the planet is a solid core. They think it's like solid metals down there. Outside of that is liquid. It's actually like thousands of kilometers of like actually melted like metal and stuff down there. This is left over from the early history of our planet when it was all molten inside. It's been cooling off for billions of years, but there's so much heat in there that it's still there. And another interesting thing, the moon going around the Earth, because of gravity, the moon kind of pulls on the Earth just while, at the same time that the Earth is pulling on the moon. And that pulling force creates some movement inside the Earth too that also creates heat. So this, like say this is a mountain here. You see all the brown mountains. I think the deepest we've ever been able to actually like dig a hole into the planet is only like 12 kilometers, which is really, really deep. Question here, mantle. What is the mantle? The mantle is just the word for the upper surface here. This is another fancy word, but lithosphere means the very top crust of the Earth, the cooler part of the Earth right here. Below that, the mantle is like the next layer of the Earth. If you imagine, who here has ever had like one of those like a gumball, and as you suck on the gumball, it changes colors. Like the outside might be speckled, you know, like white with speckled colors all over. The longer you suck on the gumball, you get down to a different color. The Earth is the same way. The most outer part of the planet has the oceans, has plants, has mountains, everything that we know. But beneath that is like layers of rock. That below that is more layers of like hotter rock that over millions of years that rock can move around. It looks mostly solid, but it's hot enough that over a long period of time, it can kind of act more like a liquid. If you imagine something like really cold honey, if you took some honey and you smeared it on the wall, you might not see it move very much, but if you watched it for a long time, you'd see it start to slowly like slide down the wall. Well, the rock inside the Earth is the same way. It's hot enough that it can sort of move over time. It can kind of flow like a liquid. But in the short span of our lives, you know, we won't see it move very much over time usually. Yeah, so the uppermost surface is like the coldest part of the Earth. And yeah, as you get inside, it gets hotter. The mantle is hot. The outer core is so hot that it's like liquid. The inner core, we're pretty sure it's solid, but still very, very hot down there, very high temperatures. Matthew, yes. So it's kind of like it gets hotter the further that you go in. And Ron Beer, yes, the Earth is actually like a huge candy. Very good analogy. Eleanor says the last picture looks like a piece in the movie called How to Train Your Dragon. Oh, okay, yeah. And there's also in some movies, there's like lava planets and stuff. Like in Star Wars, there's a lava planet. Kind of looks like that too. Yeah, so a question a lot of people have is how do we know that this is what the Earth looks like inside? If we can only dig down a little bit into the lithosphere, the outer edge of the planet, how do we know? No one's ever been inside the planet. No one's ever been down here. So how do we know that it doesn't look like this inside? How do we know that there isn't big, giant, open, hollow spaces? How do we know that it's like molten rock and then solid metal and everything? Well, it comes down to basically because VS says because of mining. Well, we can dig down a little bit, but no, we can't dig down this far. Like this layer is 2,900 kilometers down. We do not have anything that can dig that far. We're not able to go look with our own eyes and see, oh yeah, look, mantle, outer core, solid core. It's way too far down. It's probably way too hot too. It would probably melt anything that we tried to drill down there. Well, we know because of sound and sound vibrations. There is here's an analogy. In our school, we have this space called the breezeway, which is basically like a long hallway between our dining room and another part of the school. And I noticed a while back that as I walked down the hallway, my footsteps would sound like normal, like bah, 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 bah. And then I would get to one part of the hallway, and it would be like boom, boom, just your footsteps. If you really pounded your feet, it sounded different based on where you were in the hallway. And it turned out, I talked to somebody about this, even though it's on the ground floor, certain parts of the floor underneath, there are passageways that have like wires and pipes and stuff like that. They're sort of like the spaces where the people that built it, they built places for the pipes and things to go. Now, I can't see down there, but I can hear, based on the sound vibrations, that what's underneath my feet, what's underneath the ground, sounds different based on if I pound on the ground, there's more of like a flat sound, and then there's more of like a hollow booming sound. You can tell exactly where that passageway is if you just go, if you stomp your foot all the way along, you can tell exactly where that passageway starts and ends. Well, in the same way, scientists have for a long time been figuring out how to use, this is a very complicated picture, by the way, with all like the little letters and symbols and stuff, and we're not going to try to explain all that. All I want you to understand is this is like the globe has been cut in half, because it's more like that, yeah. The globe has been cut in half like that, and what these blue and red lines are is like right here where this white dot is, there was like an earthquake. And they have places on the planet that are sort of like listening stations. They have machines that can kind of feel the vibrations or listen to and measure the vibrations. And when the earthquake happened, they could measure the vibrations going through the planet and see like how long it took them to get there, how powerful they were. And what all these blue lines and red lines are showing is that they could kind of measure how fast the vibrations move through the planet, how the vibrations kind of bend as they go through the planet. And using science, they could figure out what the Earth would have to be like inside to give them those measurements. If you kind of took a big rock and you bang on it on one side with a hammer, if the rock is solidly one type of rock all the way through, your measurement on the other side will look one way. If there was different types of rocks inside, like maybe you have a big metal core in the rock, the vibrations will go through it differently, and you'll get a different measurement on the other side. Scientists have tested this enough times that they know what the inside has to look like to give them the measurements that they're getting. If on other planets, if we had the same kind of equipment, we could probably test the middle of Mars or Venus or other planets. Through other methods, we also have a pretty good idea of what we think those planets look like on the inside. But it may never be possible to go down and look. We're just going to have to use our best measurements to have a good idea of what we think it's like inside. All right, so here's another picture of the Earth kind of cut in half. And this part in the middle here is called the mantle, and the middle here called the core. Convection is a kind of fancy word, but I think we need to talk about it to understand how all of this works. Convection basically means that based on heat, things are going to move around. As you might notice, like in a room with a heater, where the heater is, hot air will rise and it'll spread around. If you sat in like a really cold room and you turned a heater on, you might notice if you sat in a different part of the room, that cold air starts coming down and you might feel a little of cold air pushing on you. So as the hot air rises in one area, it's going to push the cold air out of the way. You're going to have sort of like a flow of air. Well, the same thing happens in liquids, and the same thing happens even in solid rock over long periods of time. So the core, where it's the hottest, is sort of heating up the mantle, this rock that's almost like liquid rock. And underneath the crust of the Earth, it's actually flowing and moving. These arrows here are showing that the rock gets heated up, and it actually over long periods of time moves and flows. It kind of flows in big circles. Rayanch asks, so heat moves air and rock, right? Yeah, heat moves everything. Heat will move liquid, it'll move air, it'll even move solids over long periods of time. Like the ocean has ocean currents. Up at the poles, the North Pole and the South Pole, the really cold water up there sinks down. And that sinking motion has to pull more water in from further down the Earth where the water is warmer. So the temperature of things actually creates this movement and this flow? Well, when you have a flow of rock beneath our feet, you end up with the surface of the earth will not stay in one place. The surface of the earth is kind of like a puzzle. And it doesn't look like this, but a puzzle where you have one surface that's kind of cut up into pieces is actually a pretty good representation for how the crust or the surface of the earth works. It's just not cut exactly like this. The surface of the earth looks more like this. These lines, you can't always see them, but these lines here are the puzzle pieces of our planet. So to show that earlier slide again, we have this movement underneath the surface of the earth. Heat is warming up and making the rock flow like a liquid. And what that does is it cracks the surface of the earth. These are all sort of like plates of colder rock, in a way almost like floating on top of more liquid, hotter rock underneath. Now again, it's not, the layer below us is not like a liquid. It's not like a swimming pool. You couldn't jump into it. It's still rock, and it still would look pretty solid to us. But it's hot enough, and it is liquid enough that the surface of the earth kind of slides and moves around on it a little bit. Euron or Yirant, you're taking notes? That's awesome. I love that. Thank you. So we have been able to measure and take observations of where all of these cracks are, and like where all the edges of these plates are. And these are called fault lines. So wherever there's one of these lines, it goes all the way around, like the Pacific Ocean, which is over here on the left side of the map. The Pacific Ocean is the biggest plate. It's basically one huge piece of, like, if the earth was an egg, this is the biggest piece of eggshell of the cracked earth. There are other big plates like over Africa, over North America, over Europe and Asia. They have big plates also. There are also like a lot, these are called they're called like primary plates, I think. There's also like secondary plates, which are smaller. And then there's even smaller pieces. Like over on the east side of Africa, there's a plate here. Over India, there's a plate. I want you to notice really quick, over India, you'll notice this line right here is kind of the line of where the Himalayas are, the Himalaya mountains. And that's really important. We'll come back to that in a little bit. Rayansh says, I filled a page for my school exam. Awesome. Cool. So yeah, there are all of these plates. There are big plates, smaller plates, and little tiny ones. Like you'll notice right between the Pacific plate here and this plate next to South America, there's these like little tiny ones. And that's just like what scientists have been able to observe. Now in this picture, this is showing you, again, the plates. Now they're different colors, so just so you can kind of see them, apart from each other. The Pacific plate, the North American plate. Below North America, there's the Caribbean plate, South American plate, Antarctic plate. All these plates, they kind of fit again together like puzzle pieces, but they're moving because of those convection currents under the surface of the Earth. That hot rock flowing and moving makes these plates on the surface of the Earth want to move around. And the red arrows here are kind of showing you what direction they're moving. So in some places, like right here, the Pacific plate is kind of moving away from the Nazca plate. Down here, it's kind of moving away from the Antarctic plate. So if these ones are moving apart from each other, well, on the other side, you have to imagine if it's moving away, it must be pushing against something on the other side, and it is. It's pushing against the North American plate over here. It's pushing against the Australian plate here and here. All these red arrows you can see in other places. The North American plate and the Eurasian plate are moving apart from each other. They go right through the middle of Iceland. And there's actually a place in Iceland where I saw this in a show on Netflix. You can go there and see the place where the plates are pulling apart. There's actually like a giant trench in the ground where the plates are moving. You can see this stuff all over the Earth. Matthew asks, what does the plate mean? Well, again, plates are like big flat pieces of something. The surface of the Earth has these giant big flat pieces of crust of the surface of the Earth, and they're always moving around. And there's a lot of evidence for this. Scientists have been able to measure this. And we know that because of how things are moving around right now, that all of the continents that are above the oceans were probably in different places a long time ago. This is a picture of a long, long time ago. All of the current continents, scientists think that they were all kind of smushed together. And one of the pieces of evidence for this is that fossils of ancient animals would cross over. We found fossils for this animal in South America and Africa, and where this like yellow area is. Fossils of this plant here, of this type of fern, have been found in Australia, Antarctica, India, Africa, and South America. They wouldn't really be able to find that fossil in all of these places unless this plant was kind of spread across an earlier continent. These animals, like this reptile here, it was too small to be able to swim across the ocean. If you know, South America and Africa had always been this far apart, there's no way it would be able to swim across. But we have fossils of it here in South America and also in Africa. So that's pretty good evidence that South America and Africa used to be right next to each other. It lived in both of these places. Ethan says, isn't the Earth round? Yes. The plates are kind of flat, but they're curved too, Ethan. They're not perfectly, when we talk about flat plates, we mean like flat on the surface of a, you know, round shape. The smaller ones would be more flat. The bigger ones definitely do curve more, like, you know, like the Pacific plate being the biggest one curves more than any of the others. It's kind of like if you imagine an eggshell like that gets cracked, the smallest pieces would look pretty flat. The bigger pieces of cracked eggshell, you could see the curve of the pieces more. So yeah, Milo's, you're right. One of the names for these earlier continents was Pangaea. There's been some other ones for different sort of combinations of how the continents used to look. Yeah, you're totally right. Okay, so like in this picture, if the continents, or if the plates are constantly moving and bumping into each other, what happens when they bump into each other? Well, there's a few different things that can happen. I want you guys to imagine cars bumping into each other. Let's say you have two cars and they're going right at each other and they're going to collide. What are the different things that the cars can do when they bump into each other? Well, the cars could kind of go, and like both of their bumpers could go down and the back ends of the cars could kind of like, you know, fly up a little bit. That happens sometimes when cars run into each other. Or both cars could kind of bump into each other and their bumpers go up. That happens sometimes when cars run into each other. Or one car could kind of go up while the other car goes down. And this is a pretty good analogy for what happens when pieces of the crust of the Earth run into each other. This is one example of, like, this on the left is one piece of one plate running into another plate. But one is pushing down into the Earth, the other one's pushing up, because it's more like that from what you guys can see. And look what happens up here. When one piece of the crust is getting pushed up and up, it creates mountain ranges. Here's a map of, like, this is Seattle, down here would be like Oregon. Over here, there is a plate that is actually pushing down underneath the North American plate. The North American plate is kind of pushing up. It's called the Juan de Fuca plate is pushing down. Down here, there's actually that one image of the two cars kind of going up. The Pacific plate and the Juan de Fuca plate, they're sort of pushing together like this and kind of pulling apart at the top. And over here, the Juan de Fuca plate is going underneath the North American plate. And here, remember when we said how the plate that India is on, it kind of ran into the plate that Asia is on, and where those two plates ran into each other, they pushed up and up and up and up, and they created this giant mountain range known as the Himalayas. Lots of other mountain ranges are formed like this, either plates running into each other and pushing up, or one plate going underneath another plate, but where one plate goes up, it forms a mountain range. Here's another picture of two plates can kind of pull apart from each other. Those, again, the convection currents underneath are kind of going up and apart, and it kind of pulls the plates apart. This is like in Iceland. You can see this on the surface of the Earth. Sometimes they're really small, sometimes they're bigger. But this is like a picture of, this is actually like a spot where the Earth is pulling apart. Usually it's only like maybe an inch or a couple inches a year. Sometimes it's more based on how quickly the plates are moving. But on a long scale, a long period of time, you can see the Earth changing from these forces. So the other thing that can happen is that two plates can kind of slide apart from each other. And it looks like this. They usually call this like a strike-slip fault. You can actually see here from the colors of the rocks that like the red line here, and then like the blue and green underneath it, they used to be more lined up, and then the two plates kind of slid apart, and now they look like that. The arrow here shows that this chunk moved up, this chunk moved down, and here's another way that you can picture that. Push your hands really hard together, like as hard as you can, okay? This is like two plates kind of being pushed together. And now let's say, push them really hard together and then try to move your hand up. Like you can try to move it like this, or you can try to move one up. What do you notice? Well, your hands, just like plates, they're not perfectly smooth. They have ridges, they have parts that go up and down. So when you push them hard together and you try to move them, they'll sort of build up energy, and then suddenly it releases. There's all this pressure building up and up and up, and finally it slips, and there's like a sudden release of energy. Well, when two fault lines are pushing against each other, like a slip-strike fault here, when they want to slide that way, they'll often build that pressure up, and it builds up and builds up and builds up. And when it finally slides, it's a giant release of energy. It creates a bunch of shaking, and this is what we know as an earthquake. Earthquakes are the plates of the crust shifting suddenly and releasing some energy when they've been building it up for a while. That picture a few slides back of, here we go, of the Juan de Fuca plate moving underneath the North American plate. This is something that actually concerns a lot of people that live in the Pacific Northwest, because scientists know that this plate moving under the North American plate has been building up energy for a long time. And it's really hard to predict when, but scientists know that it's got to release that energy eventually. There's one sliding underneath the other, and they're kind of at the stage where they're like pushing really hard, and it has to give up some of that energy. When that happens, there will probably be a giant earthquake here in the Pacific Northwest. And the various problems that come with that are, in addition to being like giant earthquakes, it can make that motion underneath the water, can make like big tidal waves. It can make a lot of problems. But knowing that this is coming, people can try to prepare for it. Ethan's asking, in that picture with the flowers and stuff, where is Asia? I think you're talking about, I gotta go way back. Here we go. They don't have Asia in this picture. They're trying to show, these are like the southern continents. They don't have North America, but that would be like up here. Asia and Europe would be up here. They're just trying to show that these are like the habitats of some plants and animals that they used to, when like these continents were connected, these colors are where they lived, so that when they sort of separated apart, you know, we can tell that they lived in all these places. So I hope that helps. Okay. So yeah, these are the different types of fault lines, and we've measured them in a lot of places. Like this is in California. California has a really famous fault line called the San Andreas Fault. It's really long, and it's a strike slip fault. It's where you have two pieces of the crust are trying to slide past each other. This fault line goes, you know, there's fault lines that go right through Los Angeles, and this fault line is really famous because it has a lot of earthquakes. It has released a lot of energy over time, and you know, people in California, because this fault line goes all the way up and down California, they're pretty used to experiencing earthquakes in this area. Aubrey says, hey, Long Beach. Via says, I've gone there before. Yeah, I used to live in Los Angeles, and there were several earthquakes while I lived there. It's just sort of like a part of life when you live there. Now, the other thing that can happen when you have pieces of the crust sliding against each other and it creates a lot of heat is volcanoes. Volcanoes are places where that hot rock underneath the surface of the earth actually has a place where it can come out. If you remember that picture of the Pacific Plate, this is also called the Ring of Fire because there are a lot of places all along this red line here where that hot rock underneath the surface of the earth comes out in the form of volcanoes. Up and down the Pacific coast, the mountain range that we have here, a lot of the mountains are actually volcanoes. In Oregon, we have Mount Hood, there's Mount Rainier, there's a lot of other ones through, you know, Washington and Oregon that they're dormant right now, which means that the volcano is kind of asleep. But we know that they could sort of wake up one day and there could be, you know, they could turn back into a volcano. Well, they still are a volcano, but if they went active, they could actually have like lava and have explosions. So it's just something to know living in these areas that because of this fault line, we have a lot of volcanoes. We have a very active geology around us. So, all right, we are out of time for this class today. I hope you guys enjoyed talking about plate tectonics, the way that the crust of the earth is formed out of these big pieces here. So thanks for watching. Again, we wanted to let you all know that there are only a few days left. If you would like to do a tour of the school and see where we're broadcasting from, you can schedule a tour. A few people already did this and they had a lot of fun getting toured around by Ananya. But I think we're only going through Friday with tours. Today is our last day of classes, but if you want to get a tour of the school, you can still do that for a few more days. Just go to this